Swayam Prabha. Digital India. Educated India.
Okay, let's get started then. Let's move on to nonlinear response. Nonlinear response, better than T. All right. So to calculate nonlinear response, we already defined the system, the Hamiltonian. That's not going to change. What you're going to change is only the diagram, right? So we need to redefine the diagram. So let's do that. Always a problem with my mouse. Where it is. So I start again with some DG. My generator, third thing. Need to, let's say we set the condition, for replacing drums. So what is the refacing condition? Anybody? Phase matching. Minus K1 plus K2 plus K3. So it is basically, I could say, if I'm doing this, I have going from the bra first and ket, and then I could have the same ket, right? For example. So I need to set my phase discrimination now. Okay. So the first one, I'm acting on the bra, then the ket, then the ket. You might say, what about from the last interaction from the other side? I mean, it will take care of it. That's a great thing about UFS is it's smart enough that it will figure out all possible patterns. Yeah, you just need to set this condition and then it will figure out the other permutations as well. So you just need to set, okay, this is minus K1 plus K2 plus K3. That's what you kind of put it there. And then it will figure out all possible diagrams. Yes. Or even more if the system has more. That it will do reasonably well. So don't worry. And we will set the pulses now. So by the way, I kind of defined what this is. This is simply the pulse width sort of, right? So you have the pulses, you need to have some kind of width to it on the pulse interval. So basically that's what you're doing. Steep pulse is -1 to 1. And you multiply by 4. You have 3 field interaction, but you kind of also want to see what happens afterwards. So there is some detection time, which it will integrate over afterwards, but we need to define that. And if you remember yesterday, we wrote 8 diagrams for refacing, but then you can kind of club them into 3 primary kind of diagrams, right? At the end, downside bleach, excited absorption, and coherence. And especially for a 2-level system, you'll have only those 3 contributions. Everybody agree with me on that? There are 3 contributions, right? Agree? So for now, for generating diagrams, we just need that 3 classes of diagrams, let's say. We call one R1, R2, R3, groundset bleach, excited absorption, and coherence term. So let's say we want to create this at different interaction. So you will have field interaction at 0 time. Let's say at 100 femtoseconds, the second pulse comes, and then 200 femtoseconds, your third pulse comes, and then you measure at 300 femtoseconds. Your observation is there. As I said, you will integrate that, but for sake of generation of the diagrams and ensuring time ordering, you need to define this whole thing, right? So to do that, we will define, copy this. So for getting the diagram, creating diagrams for pulse arrival times 0, 100, 200 and detection time, let's say at 300. You can kind of then play around and see what happens if I change detection time. Not much, because it doesn't matter for the diagram. Eventually the QD-Pi calculation and QT calculation kind of takes care of that. But for UFSs, you need to define this. Okay. Pulse width, you need to change these numbers here. You can go from -10 to 10, then it will be about 20th of the second pulse. So we know these R1, R2, R3 are all the refacing pathways. That. Okay. Same way we can define non-refacing, which will also have three major classes, major diagrams. Under each class, you can generate more, but you don't need to worry about that. It will take care of itself. So here, the only thing that we need to change for calculating non-refacing is again the phase discrimination. So in non-refacing, you're going to go from ket, bra, and then ket, right? So that's what changes here. First interaction is from the ket, then the bra, then the ket. Again, same thing. You'll have three things, so I kind of call it R4, R5, and R6, 0, 100, 200, 300, and these are the replacement parameters. Let's run this. Hopefully, no problem. Okay. We can even verify these diagrams. These are the different diagrams. Tuples. We'll later see that there is not a major issue in how you define this. You need to put some numbers, you can put whatever you want. Because later on, the way QD-Pi works, it just needs that tuples at the end and it will manage. So you don't need to worry too much about it. Again, you can go and try and change what happens if you change those parameters. You can kind of think about it later. That's a good question. I think the reason is this: there is a bit of compatibility issue between UFSs and QD-Pi, and so we have the specific diagram has to be different. Thanks for bringing that up, but that will be fixed hopefully soon, so we should not have a problem. So whatever. So there is a specific kind of diagram sets this UFSs generates, and QD-Pi needs that in one. It takes in one particular way, and so we have to define this particular way. Really doesn't matter. Flip, yeah. For now, you just need to know that you can just copy this particular format. So you're going to calculate mostly refacing and non-refacing. Let's stick with that. I would, from here, this class, what you learn, the diagram generator, I would keep it the same. Don't change that part, but rather try to see what happens if I put different Hamiltonians. That way you will learn, okay, for different Hamiltonians, how my response is. Right? So I would focus on that. If you're interested, I would strongly recommend going to source code of QD-Pi and see how QD-Pi takes the diagrams in to calculate the response functions. There you can learn, if you want to really explore higher other nonlinearities and other nonlinear responses like two-quantum response. It's still, remember, it's not super user-friendly yet. I would strongly recommend if you want other nonlinear response functions, go kind of explore those aspects. Okay, everything fine? Let's go. Let's move ahead. Everybody got it? Saw the diagrams? Okay. So I kind of said these times are kind of okay. We have to set them to get the time ordering right, but those actual numbers will not be used in the actual simulation. That is only some numbers for time ordering in this particular diagram generator. Okay, the actual time ordering, actual times of arrival of each of those interactions has to be set in your actually that's kind of done within your PewDiePie. Again, you can use diagram donkey to kind of verify what happens for different arrivals. For example, for R1 diagram, I just inputted 0, 100, 110, 210 as my times. And those are, I think, more critical than anything else. Diagram donkey is such that you just need to put one thing. So it kind of system kind of knows, okay, these are my initial conditions to start with. It's probably not the best way to still do this, but that's okay. We need to find more elegant way to give inputs, which we will do at some point. Okay, so diagram donkey will generate impulse response functions basically, right? And then you need to calculate your coherence response. You might ask, okay, I'm doing only for R1. What about R2, R3, R4, R5, R6? That's fine. Even if you don't run diagram donkey, the function called coherence 2D, that is the actual function PewDiePie uses. Again, read does that, so it's fine. The only thing is coherence 2D does not have these values kind of available to it. So I would always run system donkey so as to define my arrival times and then calculate stuff. So there are two different arrival times that I have defined. One in QFSS to system generate my thing, but that will not be carried forward to PewDiePie, unfortunately. So what I would do is you put the time ordering there, but those numbers are not the most relevant numbers. And then once you define, you've gotten your diagrams, then you go to your PewDiePie's part, which is this part, run a diagram donkey for one of those pathways, like R1, for example, and it should then keep those arrival times in head, and then you could generate a 2D coherence response. If this is confusing, go ahead and read the paper on PewDiePie and also read me. Hopefully, we'll improve this and make it more and more user friendly. Okay, so that it has all the tools. Okay, so let's go into this. A lot of things, but I'm going to put it here. Okay, generating 2D coherence response. We have certain time delays. And because you need to generate some response function. Wait a minute. Is that the time delay? I forgot. Let me come back to you when I'll clarify on how to define the time delays properly. I'm getting confused now because there are different versions. I need to go back to the source code and check, but I'll come back to that. But for now, you can just use this. Sorry about that. Scan ID, again, it's because you have multiple pathways. It just is another number kind of to say, okay, these are different scans. So the most important thing that you need to use is what is called coherence 2D. Coherence 2D is the function that you need. It takes the time delays, the total diagrams that we have, which has, in this case, I'm putting refacing and non-refacing. So I'm combining all my diagrams in there. Scan ID, which is 02. R, just set it to 1 for now. Don't worry about it. And parallel also set it to false. You can make parallel stuff, but let's not worry about it. Yeah, and so this will kind of give out the states and the dipole sort of related to your number and the coherence kind of thing. T1 and T2 are your two variables over which you kind of Fourier transform, let's say, and you append to this list because there are 6 pathways it kind of runs over all pathways. So you go from 1 to 6. That's why in total diagram you have to give which one you're looking at. There are 6 pathways. So you go from go over all the 6 pathways. And then you get, and this also you don't need to worry about it because it gets even harder. Kind of explain, how do you explain this? Oh yeah, so these will give rise to the states on the dipole, and then the response is calculated here. The response list, and you kind of take the dipole and minus I, the dipole, is your response. Then you take, and there is this thing called system.spectra that actually calculate the 2D spectra. So basically what it has is the Fourier transform of the response function. That's what it does. It takes, I can give this np dot imaginary of the response list, which again is the dipole. Again, there's a reason why we do this. Let's not worry about that. And the resolution is set to be 1, that you can change. That's a temporal resolution, or sorry, spectral resolution that you want. It automatically adjusts stuff. So we need to basically then plot this spectral list, that's over E emission, E absorption, for all possible pathways separately, and that's what the multi-plot kind of does. So if I were to go over this, it's a complicated thing. The most important thing for you is first calculate your coherence 2D. The coherence 2D will generate your 2-dimensional kind of temporal interferogram, if I may call it. So remember that when you do the experiment, you're actually calculating your nonlinear response function. Right? Sorry, you're measuring the nonlinear emission, but when you're calculating, there is no way to calculate that, right? So it kind of is going to come up as a 2-dimensional interferogram because it's both will be time oscillating things, and then you do a 2D Fourier transform of that. Okay, so this gives you that the 2 time axis, and of course you'll have both the dipole and the states. We are interested in only the dipole because that's what the final emission, coherent, which is emitting mostly. And you take that and then you calculate your spectra here. Okay. Now if I run this, now I can kind of, that's everything, but you could also calculate plot refacing and non-refacing separately. Let's do that. So this basically takes refacing spectra in the spectra list. They are the first 3 are the refacing spectra. I just take that and I add all of them. So all the 3 refacing excitation pathways. So there are 3 possible R1, R2, R3. I calculate the spectra associated with R1, R2, R3. I combine them. That is my total refacing spectrum. And there is this amazing thing called Silva plot. It's a function which enables you to plot this thing in a very nice way. Slightly different from this multi-plot because it kind of ensures. So remember that you are in the rotating wave approximation, which means that when you do Fourier transform, it will all be 0. You need to appropriately translate it to right frequencies depending on energy distribution. So all that it does and plots you in the right quadrant and so on and so forth. Because remember, there's also some kind of convention. Refacing has to be plotted with my excitation as negative and absorption as positive, whereas non-refacing has. So the Silva plot function sort of takes care of all those conventions, translating it such that it's no longer in the rotating wave, but actually in something. When you're measuring, you're not in the rotating wave. You're going to measure it at some point at a finite frequency, not 0 frequency. So with all that, it kind of takes care of it. A bunch of things, but these are all mostly plot, let's say, function plot properties. We also plot diagonals here. Same way for non-refacing from spectra list, which is calculated from here. The spectra list is calculated, which is using the function spectra, which takes a response list from basically uses a dipole, which is calculated from the coherence 2D. So that's a kind of pathway for it. So what Silva plot does, so in the non-refacing, we take the other three of the spectra list, and then just add them up, and then plot the non-refacing spectrum. Okay. Kind of a very quick introduction to these functions. They all look complicated. The reason it's complicated, a bit complicated, because it has not been it's still under development. If you don't understand anything, just use this kind of things, syntax which is given here. If you want to understand, I would again encourage you to go and look at the source code. Okay, so there's a bit of improvement that needs to be done. Okay, let's calculate this. Okay, a lot came up. That's not the right ones yet. That's not been. Remember, these are our system responses, impulse response functions, Fourier transform directly, which are not the signals that you are measuring, right? So these are the system files that are here, right? The spectral list. These are the spectral list for R1, R2, R3, R4. It has not been kind of separated out and added up for refacing, non-refacing. Sometimes they cancel each other. We have to be careful of that. So it's not done for that. By the way, this is calculated considering our system Hamiltonian. So it's not, our system Hamiltonian defines this particular depth. And if you go to the response function, that's your R1, R2 real, imaginary, R3, R4. And this is the R refacing, the final plot. And what you see is a feature here. Now it's slightly off diagonal. I think that's a glitch in the code again. It's not perfect, unfortunately, but this is absorptive line shape, pretty much there. This slight shift, I think it's an artifact coming from the Fourier transform, which can be fixed. It's not real. This is the real part, imaginary part, and the absolute value kind of looks similar to what we have seen yesterday using analytical functions, right? But this is not solved using analytical formalism. It is solved by taking a Hamiltonian, using Q-tip to solve your equation of motion, and then estimating a response function. You're kind of getting what you want. This is real, imaginary, and absolute of refacing. And same way you can see real, imaginary, absolute of non-refacing. They exist in two different quadrants, as you would expect. There's still some kind of fine tunings that can be done in plotting, but you are able to calculate the response function. Okay. So now briefly for the next 15 minutes, I'll give you this code. Go around, play with it. We have gone through very detailedly the 1D response. I will leave for you to go over the 2D response carefully. The two important things is coherence 2D function and the spectra function. Spectra function is the one which the coherence 2D is kind of taking care of calculating the impulse response functions carefully, right? And impulse response functions carefully, and spectra is doing all the Fourier transform and actually getting you the measured response. Okay. Then you can add different contributions, and you want to club all the refacing together, non-refacing, all the terms together, because experimentally you cannot distinguish all the refacing pathways and non-refacing pathways. They all come together. Then it's all about plotting. Okay. Fair enough. Fair enough. Okay. So let's kind of see a few examples right now. Using this. This is just a single state. Now I want to quickly go to something else. Let's see if I put this here. Okay. Here what I want to do, I'm going to change my system now. I'm going to change my system. Now I consider two oscillators. Okay, I consider two oscillators. E1 and E2. Okay, one is at 1 and the other is 1.1 electron volt. And here the two oscillators have some kind of coupling. Okay, and that coupling, like it's negative coupling, attractive coupling, minus 0.5. Okay, it's like two molecules, like yesterday case, they can couple. Looking at the numbers, what do you think? We are in a strong coupling or a weak coupling condition? What do you think? So E1 is 1 electron volt, E2 is 1.1. Your coupling is minus 0.5. electron volt. Would you? Strong coupling. Kind of not in very weak rigid. It starts to interact much more strongly. Now what I'm going to do is, now I need to put dipole strengths to it. So I put dipole 1 to be 1, dipole 2 to be 0. What does it mean? No excitation, I mean, it's written there, but what does it mean is, no excitation means what? It doesn't have a probability to excite this coherence using light, right? That's what it means, right? Light can be resonant. I don't have any dipole moment, which means I cannot, if I take that molecule, I cannot excite it with light. Mu dot E is not going to generate a coherence. I'm not defining the light bandwidth here. I'm defining the mu to be 0, which means that there is no dipole coupling the molecular excitation with light. So I take the molecule or what, a chromophore. I have my ground state and excited state. Okay, they're orthogonal states. Now, to generate a coherence between them, I need a perturbation that is coming from light. Okay, and that we have shown in one of the very early classes. That is driven by my dipole moment operator. Okay, whose amplitude is my dipole strength of my dipole, which is kind of related to polarizability. Let's say my mu is 0. If the mu is 0, I cannot use light to create that projection. I cannot create a coherent superposition of these two states or generate a coherence between these two states using light. I don't know. Basically, it's you take this molecule, it doesn't exist. You'll try to look at it, it doesn't exist, even though the energy is there. Okay. It's kind of a very unrealistic system, but you can kind of say, you can kind of go to the condition where I have a very weak cross section for something, where it's like if you have done absorption measurements, you could sometimes see where the absorption coefficient of some of the things is extremely small. And that's probably because maybe a symmetry forbidden transition, some dark state, some triplet state, for example, or certain kind. Then you will not have, by symmetry, dipole operator cannot couple. In that case, the dipole strength is 0. So on and so forth. So in principle, if I have something like this, then I should not be seeing anything. But let's see what happens. So here I define my lowering operator. I have two systems, right? Two molecules, two chromophores. So I need to define two lowering operators. I define A and B, similar to what we have done later. And the full lowering operator is given by this capital A. That's your total lowering operator of the full system. And the total dipole moment operator is given like this. Of course, here mu2 is 0 for now. Let's see what happens, and then we will see afterwards. And your basic Hamiltonian, of course, is given by omega 1 A dagger A plus omega 2 A dagger A multiplied by h bar. That's good. And this is the coupling term. This is the coupling term that you add to the h, which is some j, which is the coupling constant, times A dagger B plus B dagger A. So most of the coupling is going to always look like that, where there is this coupling which mediates annihilation of one and creation of the other, or annihilation of the other and creation of the other, quantified by G. Okay. All right. So that is my system. I need to create my collapse operators. I do exactly the same way, but only thing is now I need to define 4 operators, because I have 2 different systems, right? 2 different subsystems, I call it, right? Corresponding to my lowering operator A, lowering operator B, with energies 1 and 1.1. Again, the same kind of relaxation operators. The only thing is I need to have 2 thermal populations here, N1 and N2, and then I create my collapse operator list. Okay. So, and my system setting up is exactly the same. Now, because you have 2 subsystems, you need to take the density matrix of one, which is 2 by 2, density matrix of the other, which is 2 by 2, and then do a tensor product. Then you create your final density matrix. Okay, fine. So that's what we do here. This is the expectation value of this. I did do a Fourier transform of that, but that's fine. Linear response is probably boring. Nonlinear response, again, the same way we define our set the phase discriminator to be having the refacing diagram, combine them all here, generate diagrams. This is our non-refacing diagrams. Very good. And then we go and calculate the response. Let's go and see the response. Let's look at the final refacing response. And what is this the right one? I would have expected something else. Let me rerun this. Okay, so now you see, I started with a condition, right, where I take two states, right, and I say one state doesn't have any dipole, but I can couple to another state. If it doesn't have a dipole, right, if I take two systems, one is absorbing, one is not absorbing, what you would see? You would see only one transition, right, in absorption. Same with 2D, you should see only one. But here what we see? We see two diagonal peaks and two cross peaks, which means you're generating two states. Where are these two states coming from? Through the coupling. When you mix, you're going to kind of transfer some dipole strength to the other one. You couple them, even though other one does not have much, right? Got the coupling strength. And then you generate two states now. So remember, when you define the Hamiltonian, we are diagonalizing the Hamiltonian, right? When we define it, when you define the system, we said diagonalize true. In that diagonalized Hamiltonian, you will have these two mixed states, which have character from both. And so each of them will get some dipole strength coming from our one molecule, which has dipole strength, but it will kind of inherit that. Okay. And then you will see peaks on the diagonal and off diagonal. Does it make sense? And of course, if you see carefully, there is a large splitting, and these don't really appear at where they're supposed to appear. That's because you have large splitting between those two states. So you take two states which are close by and you generate new states, which goes up and down. And that's what they appear. Now let's quickly see what happens if I reduce my coupling constant, right? So this is a strong coupling where I take two states, one doesn't have a dipole, mix them, and we produce new states. Now let's see what happens if I go back and change my system. Let's say I make this very small. Okay. If I do it very small, I would expect to see maybe one state, right? Because the other one is not coupling, is not going to see light. And also I will see a shift in the frequency because I'll see at around 1 electron volt where it's supposed to appear. So let's run this. Okay, the system has been diagonalized. Let's directly go and calculate our nonlinear response. This is already done, so we don't have to run this again. Okay. Run this. There you go. What do you see? Only singular transition. That's because there is no coupling between the two. Okay? Make sense? So you're able to capture that nonlinear response pretty well. Now, in this condition, in the weak coupling condition, let's say I give some dipole strength to the other one. What would you expect? They're weakly coupled, but I'm putting some dipole strength. Don't look at this, it has to not right now. You still have some cross coupling, which is interesting, which means that 0.005 is still not weak enough, let's say, to kind of, so even 0.005 is still in our system for some reason, whatever the system is saying, that we are still having some kind of coupling between them. Unlike the previous case, you see that the energy difference between the two peaks is much lower. That's because the interaction is weaker, right? So maybe if you make this 0.5 1 e power minus 6, maybe you will really go into really weak coupling limit, and then you might want to give this a try, for example. Okay, kind of get the point. So I've given these codes to you, so I would encourage you to go and play around with the codes. Importantly, go and read PewDiePie material, okay, and if you're interested, really dig deeper into this. Remember, PewDiePie is still under some kind of optimization, so it may sometimes you might find it a bit painful, but the most important thing is the D function and the spectra function in those two. In PewDiePie allows you to do this nice plotting. These three are the primary functions that you may want to use. Calculate nonlinear response. I mean, another thing, and also add another Lindblad operator. Add in whom, what is the kind of collapse operator that I need to bring in? T square over 2, right? So that's the lowering operator. So if I have collapse operator, some kappa times or gamma times lowering operator. Now, if I had inhomogeneous broadening, I add term which goes as square of my the Lindblad corresponding to inhomogeneous broadening is that. So you'll have another delta, which is the in the system, and you will see, I would strongly encourage you to do it, and very different parameters. Lindblad operator for inhomogeneous broadening. How it broadens the transition, whether it's and a diagonal, so on and so forth. So independently, your kappa and delta broadening, and then it's very so to kind of go over that and identify kind of various how various parameters. I probably went a bit too fast at the learning PewDiePie. I probably haven't figured out. If you have questions, come back to me, right? I apologize confusion there of especially the T delays and how it's done. I can give you a kind of a write-up, which I can of a summary of the PewDiePie thing, exactly what each of the functions do, okay, which I'll probably do in the next class or maybe in future. Important thing is you can just use my play around with your Hamiltonian, all the parameters. You can even if you want and see how nonlinear response functions. Powerful because now you can start out with any system path interaction that you can put in explicitly. You can diagonalize it and give PewDiePie the tool to calculate. It'll calculate. So you have that ability to explore whatever you want. Okay. All right. With that, shall we close? Any questions? Okay. Do you all did you send the file? Is it on the folder? Okay. So there are some stuff on the folder already, so you could kind of access these files. There are more things which I put in there, which I was trying out. It didn't really work out, but I put those things. The most important thing is the linear and nonlinear response for single system, composite system of two different kinds, right? So you can kind of play around with that too. Okay. Fair enough. All right. Thanks.